So recalling that we characterize stochastic processes in terms of probability models, in order to model real-world counting processes, we need to construct a mathematical abstraction which reflects the empirical properties of countable processes we observe in nature. Also, recalling that counting processes are a species of continuous time discrete state processes, this amounts to finding expressions which explain how the distribution of the count, a discrete random variable, evolves over the continuum of time. So for these purposes, we start by constructing the Poisson process from first principles, from which we then infer the underlying probability model. So for today's video, we'll start with the so-called Poisson postulates, and then we'll subsequently derive the distribution of the state variable, the count, under a standard time-homogeneous Poisson process, which obviates the origin of the name of the process. So let's jump in. So consider the following. A counting process, a set of random variables, nt such that t is greater than or equal to naught, is a Poisson process with rate parameter lambda being greater than naught if 1. N sub naught is equal to naught, so we start counting from 0. 2. The process has both independent and stationary increments. 3. The probability of observing exactly one event in a small interval of length h, so probability of nh minus n naught equals 1, is just equal to lambda times h plus terms which are little o h. Okay. Now what it means for a function, say f, to be little o h is that if we take the limit as h tends to naught of fh divided by h, then that limit must be naught. Okay, so that's what it means for something to be little o h in this context. 4. The probability of observing more than one event in a small interval of length h, so probability nh minus n naught greater than or equal to 2, is just also little o h. Okay, now we will henceforth refer to these four as the so-called Poisson postulates. You can think of these as little axioms or elemental statements which give rise to the main statistical result that characterizes the model class. Now before we continue, just make a note that the postulates, as I presented them here, pertain to the time-homogeneous case. So recall that time homogeneity loosely translates to the distribution of the process over a given transition horizon, not being dependent on where the process is in time. Now later on, we'll relax that assumption by altering the postulates. So if you're ever tasked with reproducing the postulates or a proof as what will follow, make sure that you check if it's for the time homogeneous or the time inhomogeneous case. Okay, so this neatly brings us on to the theorem from which the model class derives its name. Okay, and we'll follow the proof and outline as in the text on stochastic processes by Ross et al. It goes like this. Theorem. The number of events occurring in any interval of length t is distributed Poisson with parameter mu equals lambda t. So, that is, the probability of nt plus s minus ns equals n is just lambda t to the power n divided by n factorial times e to the minus lambda t. Okay, so straight from the mass function of the Poisson distribution. And this expression should hold for all s and t greater than or equal to naught. So over any given transition horizon, starting from some reference point, say s, the distribution of the amount by which the count increases over that interval from s to time s plus t is Poisson distributed with parameter lambda times t. Okay, so nice, neat little result. Now, for the proof of this statement, we'll use a convenient shorthand notation, also suggested by Ross, whereby we write p sub n arg t, and I will just henceforth say pnt when I mean this probability, is just the probability of nt plus s minus ns equals n. Okay, so the number associated with that increment. So that when we write p naught t, we mean the probability of 0 events in an interval of length t. Or alternatively, if we write p1h, we mean the probability of 1 event in an interval of length h, for example. Okay. Right, so that's it. Let's tackle the proof. So, as proofs go, we'll break it up into small digestible chunks, and in this case, the sketch of the proof follows 3 simple steps. Okay, so first step. We'll find an ordinary differential equation which describes the evolution of p naught t and then solve that to show that the statement which we're trying to prove is true for at least the case where n is equal to naught. Step 2, we'll find a system of ordinary differential equations which describe the evolution of all subsequent probabilities, so Pnt for n greater than naught. And then finally, in step 3, we'll solve the system of ordinary differential equations, which thus then describes the probabilities for all n, so we combine those in steps 1 and 2, using either mathematical induction or by finding an ordinary differential equation for the generating function associated with the probabilities, either of which we can then solve to show that the PNTs for all n must be from the Poisson distribution. Okay, so let's consider step 1. So this is for the case where n is equal to naught. Okay, and we'll start by looking at the probability P naught t plus h, which is just the probability of nt plus h minus n naught equals naught. Okay, and that's from the definition of our shorthand. Okay, so the probability of observing a count of 0 over an interval running from naught to t plus h. Now we can write that as simply the probability of nt plus h minus nt equals naught and nt minus n naught equals naught. Okay, so why is that? Well, if we take that overall interval from 0 to t plus h, we break it up into two sub-intervals, one interval running from 0 to t, another from t to t plus h. If the overall count is 0, then, well, it must be 0 in both those intervals. Right, so that's why we can write it as that probability. Well, then also, by the independence of the increments, we can also then say, okay, well, we can write this probability as the product of two probabilities. And indeed, we write it as P naught h times P naught t. So the probability of observing 0 in an interval of length h times the probability of observing 0 in an interval of length t. Okay. And then what we do next is we're going to substitute one of these probabilities using the Poisson postulates. And indeed, we take the P naught h, okay, so the probability of observing 0 over some small time increment h, and we write it as 1 minus the probability of observing at least one event in that interval. Okay, so 1 minus P1h minus the probability of observing more than one event. Okay, and if we substitute the Poisson postulates in there, we end up with an expression 1 minus lambda h plus terms which are little oh times all of that times P naught t. Okay, now note here that if you're confused by what's happening with the mathematics here, that little oh is a mathematical critter which gobbles up terms. So something which is times oh, so a constant times h, is also little oh. Something which is little oh plus little oh is also little oh, and so on. Okay, so just bear that in mind as we're going through the proofs. Cool. So next up, what we can do is we're going to take this equation now, okay, and we're going to rearrange it and then divide both sides by h to find P naught t plus h minus P naught t divided by h is equal to minus lambda times P naught t plus little oh over h. So terms of little oh over h. Okay, now you can almost see where this is going, right? Because we're looking for an ordinary differential equation which we can then solve, and that term on the left there starts looking familiar. And indeed, from the definition of the derivative, if we're taking the limit as h tends to naught on both sides of our equation, we end up that the first derivative of P naught t with respect to time is equal to minus lambda P naught t plus 0, where that 0 comes from our definition of terms which are little oh. Okay, and this gives us a nice, neat, simple ordinary differential equation which we can then solve for that probability. And indeed, what we do is we find the general solution, P naught t is equal to k times e to the minus lambda t, where k is going to be some constant, right? How do we find that constant? Well, we substitute a boundary condition. Okay, and the boundary condition we'll use is that P naught naught is equal to 1. And that follows since no events in 0 time occurs almost surely, and indeed, from our postulates, we start counting from naught. And that yields that k is equal to 1. So the solution to this equation gives us the probability P naught t is equal to e to the minus lambda t. And indeed, a quick check of the statement that we're trying to prove shows that the probability for the case n equals naught does indeed align with the corresponding Poisson probability mass. Okay, so just keep that in the back of your mind, and then remember the ordinary differential equation we have here. And that concludes step 1. Okay, so let's tackle step 2, and this is finding a system of ordinary differential equations for all n greater than naught. Okay, so first, let a be the interval running from naught to t, and let b be the interval from t to t plus h. Okay, so we just break up the interval running from naught to t plus h. And then we'll consider the probability of observing n events in an interval of length t plus h. Okay, so from our definition of the shorthand, we can just write that as the probability of n t plus h minus n naught equals n. Now, let's consider that interval and the way we've broken it up. If we have n events in the interval running from naught to t plus h, and we consider the two subintervals, that count can be distributed over the two subintervals as follows. Either you could have had n events in interval A and 0 events in interval B. Or you could have had n minus 1 events in interval A and 1 event in B. Or you could have had n minus 2 events in A and 2 events in interval B. Okay, so you see where the sequence is going. Okay, and you can go all the way up until you have n events in interval B and 0 events in interval A. Okay, so those are all the possible permutations of how that count could be distributed. So what we can do is we can write the probability of nt plus h minus n naught equals n, so the count being n over the entire interval, in terms of the probability of those events, of it being distributed over those subintervals. Okay, so we have it that that probability must equal to probability of nt plus h minus nt equals naught and nt minus n naught equals n. So 0 event in the interval t to t plus h and n in the interval naught to t. Or, so plus the probability nt plus h minus nt equals 1 and nt minus n naught equals n minus 1. Okay, so 1 event in interval B and n minus 1 events in interval A. And then you could carry on so on and so forth, counting up all the ors and that whole sequence of probabilities. Okay, which covers the remaining permutations of how n could have been distributed amongst those two subintervals. Now, as we did before, we just take some of these probabilities and use the independence of the increments argument to write them as products of probabilities. And then we find that the first probability in the sequence we write as p naught h times pnt, so 0 events in an interval of length h times n events in an interval of length t, plus the probability of 1 event in an interval of length h times probability of n minus 1 events in an interval of length t. And then finally, plus terms which are little o h. Now, this final term, being a set of terms which are little o h, follows from the fact that all of the probabilities in that summation, okay, have 2 or more events in a small interval of length h, okay? And by our postulates, we say that, well, those have to be of order little o h. You add them all together, that gives you something which is little o h, and there you have it. So we're going to carry along this little o h term. Right. Then, as before, what we do is we plug in the postulates for some of the probabilities on the short interval of length h, and then we'll play around with the expression. Okay, so we write p naught h, again, as 1 minus lambda h plus terms which are little o h, and we multiply all of that by p and t to get our first term. We say plus lambda h, which is just p1h, and that follows from, again, from the postulates, multiplied by pn minus 1t. And then finally we have that plus little o h. Cool. Now, again, as before, we can rearrange and divide by h to find pnt plus h minus pnt divided by h is just equal to minus lambda times pnt plus lambda times pn minus 1t plus terms which are little o h divided by h. Again, you can see where this is going. We're looking for a differential equation or system of differential equations in this case. We take the limits as h tends to naught on both sides, and indeed we find the differential or system of different ordinary differential equations. The first derivative with respect to time of Pnt, the probability of observing n events in an interval of length t, is just equal to minus lambda Pnt plus lambda Pn minus 1 t. Okay, and we say system of differential equations because this expression holds for all n running from 1 to 3, etc. And the right-hand side of that equation tells you how these probabilities along the dimensions of that system are related. So note the n and n minus 1 over there. Okay, so this general expression here gives you the pattern for a system of equations. And there we have it. We can combine the set of equations in this step, so step 2, with the ordinary differential equations for the differential equation we had for the case where n equals naught, and we thus have a system of ordinary differential equations which describe the evolution of the probabilities associated with the state variable nt, but for all n. Now, if we can solve this infinite system, we will then have our probability model for the process constructed from first principles using only the Poisson postulates. Now, what remains to be shown is that these probabilities are from the Poisson distribution. And that's what we'll do in step 3. Cool, so let's look at the final step. Now, as you may have already spotted, the difficulty with solving the present system is that we have an infinite system of ordinary differential equations, meaning that we have countably infinite number of equations. As for showing that the sequence of probabilities are Poisson, that in itself is a good thing, since the support of the Poisson is also non-finite. But how do we go about solving such a system? Well, as mentioned before, we can go the route of induction, whereby we postulate a test equation, so in this case determined by the Poisson distribution, which we suspect to be the correct expression, and then show that the statement holds for a root case, and then over an increment of n, from which we can deduce that it will hold for arbitrarily large n. Okay. An alternative route, and the one we'll be taking today, is by finding the generating function associated with the distribution, or that sequence of probabilities, which, if we can show that that lines up with that of the Poisson distribution, will then establish the result. So, here goes. So, recall that the generating function, gz, for some random variable x, is just given or defined as gz equals the sum over the support of the probability of x equals x multiplied by some dummy variable z to the power x. Okay, so expectation of z to the power x. So, for the random variable nt minus n naught, we have that gz, comma t, so we add an argument t to account for the time variable, is equal to the sum over all n running from naught to infinity of pnt, so the probability of observing our count n over an interval of length t, multiplied by z to the power n, where z is again a dummy variable. So again, just note the addition of the time argument there. That's not dummy variable, that's just because our probabilities contain a time parameter. So, we start then to find the generating function by writing out the system of ordinary differential equations we derived from steps 1 and 2 out in sequence. So n equals 0, 1, 2, 3, etc. And then we'll write down the case for some general n so we can keep track of the pattern. Next, we go in each line of the set of equations and we multiply it by dummy variable z raised to the power of the index n. So the first equation, we multiply both sides by z to the power 0, second z to the power 1, etc. And in a general case, we'll have it multiplied on both sides by z to the power n. Cool. So we have still have our infinite system of equations. Now just multiply each of those lines in this system. Well, then what we can do is we're going to add all of these equations together. So the system collapses into a single equation, albeit with infinite sums. But no matter, since, well, these expressions are now starting to look very much like the thing we're trying to get after. Okay, a generating function. We just need to manipulate the expression a little first. Cool. So we end up with the expression, the sum of n running from 0 to infinity of the first derivative of pnt with respect to time multiplied by z to the power n is equal to the sum of all n running from 1 to infinity, lambda times Pn minus 1t times z to the power n, minus the sum of n running from naught to infinity, lambda Pnt times z to the power n. Okay, now what we do then is we first take out a lambda out of each of those sums and also a z from the first summation. So we end up with lambda z times a sum running from n equals 1 to infinity of Pn minus 1t times z to the power n minus 1. So the index of those two elements now line up, minus lambda times a sum running from n equals 0 to infinity of Pnt times z to the power n. Okay, so the second summation is starting to look like something that we know. Cool. Then, as a final bit of manipulation, what we do is we take that first summation, and we want to make it look like the second one. So we just replace the index, n, and we replace it by m equals n minus 1. So we now have a summation, m equals 0 to infinity of Pmt times z to the power m. Okay, and that again now looks like the definition of a generating function. And indeed, what we can now do is we can take this expression and write it in terms of a generating function as follows. And that is the first derivative of the generating function with respect to time. So that left-hand side follows, since we can take the derivative into that summation, is just equal to lambda z times gzt minus lambda gzt. Okay. And that leads us to the simple ordinary differential equation. The first derivative with respect to time of zt is equal to lambda z minus 1 gzt. Cool. So simple ordinary differential equation, which we now need to solve. And how do we solve it? Well, we need to find the general solution and then plug in a boundary condition because it needs to satisfy the boundary condition. In this case, well, we can again use the argument that, well, the count at time 0 is 0, so gz0 is equal to 1, and we can solve that equation to find gzt is equal to e to the power lambda t times z minus 1. Okay. Now, comparing that solution to that of the Poisson distribution, so gz is equal to e to the power mu times z minus 1, we note that, well, by the uniqueness of the probability generating function, it must then be that nt minus n naught, so the count random variable, is indeed Poisson distributed with parameter lambda times t. And the proof is complete. Cool. So, in consequence, we have that the distribution of the number of events in any interval of length t, that is the probability of nt plus s minus ns equals n, is just the Poisson probability, right? Lambda t to the power n divided by n factorial times e to the minus lambda t. And this should hold for all s and t greater than or equal to naught. Now note that our proof only covered the interval of length t and we started from 0, not s, but the for all s actually follows from the stationarity of the increments. So think of s as being a reference point here again. Okay. Now, intuitively, this distributional result actually makes sense. Okay, consider the following. If you think of t as the amount of exposure time on a counting instrument, if the events occur at a rate of lambda per unit time, then on average one expects to see lambda times t events. Okay, that makes sense, and indeed that lines up with the mean from our Poisson distribution. Now, as for the probability of observing a particular value for the count, well, under the assumption that on a relatively small interval, so very minute interval, one expects events to be rare, so observing over a very small time, we only expect to observe at most like one event, well, then we can actually show by the calculus from postulates 3 and 4 that the distribution over larger intervals is Poisson with mean lambda t. Okay, so nice intuitive result. Okay, now let's cover a quick application of the probability model. So consider timing runners as they cross the finish line of the Two Oceans Marathon over a time window of around 15 minutes. If runners pass our timing instrument at a rate of 0.4 per minute, 1. what is the probability of observing exactly one run across the finish line in that time window? 2, what is the probability of observing more than 2 runners cross the finish line in that time window? Now I'll include a little simulation of the number of possible trajectories of the count process under this configuration, so you can get a feel for the likelihood of these events. But let's quickly do the calculations, and you'll see they're quite simple. So for question 1, what is the probability of observing exactly one run across the finish line? Okay, so that's just P115, right? So probability of observing one event in a window of 15 minutes. Okay, and we have a rate parameter of 0.4. Okay, so we go to our Poisson distribution, we plug that in, we have that, okay, we replace the mean with 0.4 times 15, evaluate the Poisson probability from the mass function, and then we'll see, okay, well, the probability of that event occurring is roughly 0.015. Okay, so small probability of that event occurring. And indeed, if you look at the simulated trajectories, that seems to make sense. Question 2. What is the probability of observing more than 2 runners cross the finish line in that 15-minute window? Okay, well, we can evaluate that as 1 minus the probability of observing 0, 1, or 2 runners, right? Looking at probability of more than 2 runners, so we can 1 minus the probability of 0, 1, or 2. And that's just 1 minus P115 minus P015 minus P115 minus P215. Okay, and again, well, we just plug in our parameters into the Poisson probabilities, do the calculation, and then we end up with a final value of 0.94. Okay, so it's actually quite likely that we'll see more than 2 runners cross the finish line. So, as you can see, if we model real-world processes using a Poisson process, the probability model allows us to easily answer questions about the state variable and the likelihood of events that we might be interested in. Indeed, it should now be obvious why the Poisson distribution and the Poisson process is such an important tool in the statistician's toolbox. The number of potential statistical applications is about as large as the number of natural processes which one could reasonably approximate using the assumptions, or postulates, underlying the Poisson process. And indeed, as we'll see later, it's actually easily generalized so that we can always tailor the process to reflect empirical properties of the process we're modeling if they do indeed depart from this simple configuration. So, I hope you found that interesting. I'll leave you with some exercises, and then I'll see you in the next one.